Let's get started. Okay. So, what we have been focusing on is to evaluate average or expectation and the standard deviation. Okay. Why is that? Because if we solve Schrodinger equation and then when we obtain the physical quantity, like such as energy, momentum, for example, velocity and location, it turns out it's not gonna have fixed value. Okay, it's gonna have some probabilistic distribution for those physical quantities. So then, in order to understand those physical, kind of a distribution, we have to evaluate average and standard deviation. That is why we are kind of trying to evaluate, what is the average and what is the standard deviation. Okay. So here, we were essentially we got just basic, expression for standard deviation, but there is another way of getting standard deviation by using this formula, and then we are going to kind of prove why that can be the case, okay? So as we talked yesterday a little bit, this sigma square, standard deviation square, is simply the difference from the mean square and then you take average. So in order to take average, what you do is, just difference square and then the possibility of picking j element, and then if you multiply and then if you're just summing over for all those elements, you can actually get the average. Okay. So with that, if I kind of keep continuing this one, then this one can be expressed as j minus delta j. Oh, no, sorry about this one. This is a j bracket and then square and p over j. Okay? Because, this delta j, by definition, if you kind of look up here, by definition, this delta j was a j minus average, right? Because that is essentially difference from mean. And then I'm just going to write down here. And then if we express further, like expand it, j square minus 2j bracket and then here j bracket square and p of j. Okay. So simply we are just expanding this part, and after that, if we write individual term, it will be expressed as like this way, minus 2 and j bracket here pj plus summation j bracket square p of j. Okay. So now let's look at this expression here. Okay. So now we have to kind of identify which one is constant. Okay. So look at this one. What is a constant? This j bracket. Okay. This j bracket. What is this one? This is the average, right? Expectation value. So this one is a fixed value, right? Constant. Okay. If we are given for a set of data, the average value is a known, right? And then that one is going to be constant. So this one is constant, and obviously this one is constant. Okay. So with that, let me just write down here. This is constant, and obviously this one is constant. But this j here, and then this j is all element itself. Okay, so this is not constant. So then, constant, now we can bring this out, right? So if we do that, now we can write down as, basically, like if you look at this part, this one, like using the same argument as before, this one is simply j square bracket, right? Because that is j square average. And then if we bring that out for the second term, that is a minus 2 average j bracket and then summation j p of j plus now this j bracket square, that is average, so it comes out, and then p of j. Okay. So then with this expression, what is this? Or let's start with this one. What is this? If we are summing the possibility of all the elements, it must be 1, right? Does it make sense? So in this case, this one must be 1. And then what about this one? We can express this as, that is essentially expression for average, right? So this one is simply J bracket. Does that make sense? Okay? Because you know what we are doing is that we are summing over all the elements, and then for each term we are basically writing as, you know, element itself multiplied by the possibility of picking that element, right? That is essentially same as this idea, right? This one, okay? So this one is now average here. So look at this one now, J square bracket and the minus 2 J bracket here, and then J bracket square. And then if we simplify that, it will be written as J square bracket minus 2J plus J bracket square. Okay, I'm just simply writing it down from the previous slide here. Here, J square bracket, and then here J bracket, okay, and then here. So what that means is that now this one is simply J square bracket minus J bracket square. Okay. So again, if we just kind of write full expression, this sigma square, right, that is essentially where we started, right, here, sigma square, and this will be J square bracket minus J bracket square, or, you know, if we just express in terms of just sigma, it will be square root J square bracket and then J bracket square. Okay. So what does this mean? You know, in order to find this standard deviation, if you know the mean, average, right, that is essentially where this one goes, and then if you know the square element, you know, element square average of that, you know, like you just kind of plug it in, and then you can evaluate standard deviation as well. Okay. So then now, you know, up to this point, we should be able to find out, you know, average and standard deviation of any physical quantity that we are interested in quantum system. Okay. So, and then there is actually another important concept from, you know, quantum mechanics, which is Heisenberg uncertainty principle. You know, it's a kind of a lengthy process to derive and prove that. So I'm gonna just kind of state, you know, as a just granted. So Heisenberg uncertainty principle states that standard deviation of position multiplied by standard deviation of momentum must be equal or larger than h bar over 2. Okay? So these two values, when we multiply them, it has to be equal or larger than this value. Okay? So this one is actually kind of a counterintuitive again, because of, you know, like in terms of deterministic value. Okay, so for example, if we know exactly what the position is, what does it mean for the standard deviation of position? So if we know exactly what the position is, what does that mean? You know, what does that translate to standard deviation? Standard deviation must be 0, right? If we know exactly what the value is. Does it make sense? Because, you know, like that means it's like a delta function, right? We kind of have the, you know, position here. If we know where the particle is exactly, what that means is that it has perfect chance, like 100% chance of x is, let's say, 1 meter, or something like that, right? So this is exactly, where we know what does it mean in terms of standard deviation. That is, standard deviation is a 0, right? Does that make sense? So then, what does it mean here? Like, for example, if we know the position exactly, what this value has to be to satisfy this one. It's basically, you cannot really get that, but realistically, this one has to be infinity. Does that make sense? So my point here is that if we, maybe like another way to kind of express this one is, if we lower standard deviation of position, what happens to standard deviation of momentum here? It has to go up, right? If we lower standard deviation of position, standard deviation of momentum has to go up, right? Because it has to be equal or larger than h bar over 2. Okay. So what does it mean? Physically, what that means is that in quantum mechanics, or actually it's kind of universally applicable, but we are going to talk about it a little bit later. If we know position more precisely, what does it mean in terms of momentum? The uncertainty of momentum increases. Okay? Or if we try to find velocity or momentum more precisely, what does it mean for position? We are going to have greater uncertainty. We are going to actually know less about the precision of position. Does it make sense? So that is essentially what Heisenberg uncertainty principle states. So here, let me just kind of write down here. So what this means is that the more precisely determined a particle position is, the less likely is its momentum. So, or in other words, this one basically tells us that cannot be accurately determined simultaneously. Okay. So this is a Heisenberg uncertainty principle, from quantum mechanics. And then this one is actually universally applicable. Okay. For example, as I mentioned before, quantum mechanics or Schrödinger equation should be applicable for any sizes, whether the matter is small or big. So the same argument applies here. Okay. So this one has to be applied universally, whether the size is small or big. But then you might have a question. In bulk world, in bulk scale, this is not true, right? We know exactly the position is, if we consider any object, we know the position exactly, and then we can quantify velocity or momentum very precisely, right? That is why, we are dealing with Newton's law, okay, to identify what the position is and then what the velocity is. But this one states that when we multiply these two, it has to be, minimum h bar over 2. Okay. So now, how do we kind of resolve this issue? Okay. So and then obviously, it's gonna be resolved. But here is one example. Okay. So let's look at macroscopic object. Okay. So for example, just kind of as an example, like a momentum, we are going to consider the 1 kilogram mass, and then let's say it's moving 1 meter per second. Okay. So, just kind of a bulk scale object, like 1 kilogram is about 2 pounds. And then, for bulk scale object, we can quantify velocity very, very precisely. right? Like we can quantify velocity very, very precisely. So what that means is that, you know, like it's a kind of safe to assume that the uncertainty of velocity, okay, or momentum is roughly like 10 to the 15 kilogram meter per second, okay? So uncertainty or standard deviation. This one is still very, very small, right? I mean, you know, like even with the state of our technology, we cannot even get this precision, okay? But I'm gonna just kind of, estimating this precision here. So uncertainty is 10 to the negative 15th power kilogram meter per second. You know, as you know, like this one, the 1 angstrom is 10 to the negative 10th power meter, okay? So with this number, okay, with this very small standard deviation of velocity or momentum, what that means is that we know exactly what the velocity is, right? We can safely say we know exactly what the velocity is. And then if we multiply this sigma p, sigma x, or when we apply this Heisenberg uncertainty principle, and then this one gives us sigma x is roughly speaking 10 to the negative 19th power meter. Why is that? Because when you actually look at this h bar number, this h bar turns out to be very, very small value, right? 10 to the negative 31, like something like that, right? So in the sense, or 34, so here, you know, sigma x, now uncertainty of position is 10 to the negative 19th power. What does it mean? You know, this one is actually much, much smaller than even atom size, right? So here, if you look at it, this one, these two values, extremely small. So in the sense, in bulk world, we can quantify position and velocity very precisely at the same time. Does that make sense? So, you know, like even with this Heisenberg uncertainty principle in bulk scale, you know, like since these values are very, very small, realistically, you know, it's safe to say that we can quantify this, you know, position and velocity or momentum very precisely simultaneously. Does it make sense? Because, you know, like it has to be, yes, yeah, go ahead.
Sorry, what's that 1A star?
Oh, there's an angstrom. 1 angstrom is 10 to the negative 10th power meter. So yeah, it's just kind of because, you know, like atom size is like, you know, like 1 or 2 angstroms, right? So in the sense, I'm just kind of want to give you a reference here, like how small the values are, you know, like these are essentially extremely small, like even much smaller than atom size. So, you know, very safe to say that we can quantify these two quantities very precisely, okay? So here, what that means is that we can quantify location and momentum. So, you know, momentum is essentially velocity, right? So precisely, okay? For the bulk scale object. But now let us look at microscopic object. Okay, let's see what happens. For example, you know, electron. Electron, you know, velocity is, you know, like one of a common value that we can use is 2.2, or like just in terms of order, 10 to the 6th power meter per second. And then electron mass is 9.11 times 10 to the negative 31th power kilogram. Okay. And then here we are gonna evaluate uncertainty of the momentum. Okay. So in this case, we are gonna essentially assume 10% uncertainty. Okay. So what that means is that now when we evaluate the standard deviation, so that is a 9.11 times 10 to the negative 31 times now velocity, that is 2.2 times 10 to the 6th power, and then uncertainty value, you know, like because of this assumption, you know, like we're gonna multiply by just 0.1. Okay. So again, this is just kind of a, like a just rough estimation. Okay, just to give you how this one can be applied to Heisenberg uncertainty principle. Okay. So with that value, now we are gonna apply Heisenberg uncertainty principle here. Then it's gonna be, like this expression, and h bar is 1.05 times 10 to the negative 34th power joule times second. Okay, so this one can be applied also here. Okay, so then sigma x, it turns out it has to be h bar over 2 times sigma p, and just kind of rough calculation shows you that this one is roughly about 2.62 times 10 to the negative 10th power meter. Okay. So what does it mean? This one is now 2.62 angstrom, right? So if we consider, this uncertainty of velocity or momentum, what is the standard deviation or uncertainty of the position? That is 2.62 angstrom. So in terms of like kind of atom size, like when you compare that to atom size, this one is actually appreciable number, right? So because electron is so small, so when we kind of look at microscopic object, now this Heisenberg uncertainty principle gives a big implication in the sense that like for microscopic object like an electron, you cannot really know position and momentum or velocity simultaneously. So for example, in this case, if you really kind of try to focus, find where the position of electron is, then what is the consequence of that? You're going to have large uncertainty in velocity. So if you kind of focus on position, you're going to lose accuracy of the velocity. And then if you kind of focus on just velocity, you're going to lose the accuracy of the position. So that is a kind of, the consequence. You can never get precise value of position and velocity for small scale objects. So which is a kind of very counterintuitive, but that's the consequence. Yes?
Is that due to how we measure those things, or why can
that's not related to measurement technique. It's just direct consequence of the quantum mechanics. Just kind of following this Heisenberg uncertainty principle. So this is a principle. This is a kind of applied universally anywhere. So it's a kind of length process to prove this one. But if you actually take this one as kind of like a principle, and then when we apply this to a microscopic object, it turns out that like when you decrease sigma x, what does it mean? You get more accuracy in position. When you decrease sigma x, sigma p has to go up, right? Think about this. Forget about this. This larger. Right? Think about this as equal. Okay. If this is equal, when you decrease this sigma x, what happens to sigma p? It has to go up, right? Does it make sense? Think about this as the minimum, if we are kind of aiming for that, this one can be expressed as sigma x, sigma p equals h bar over 2, right? This is the minimum value that you can kind of aim for. So when we kind of work with this expression, just for sake of explaining like what happens, when we decrease sigma x, sigma p has to go up, right? So that means, like sigma x going down, that means we have more accuracy. And then sigma p goes up, that means we have less accuracy in velocity. Okay? So this is a kind of consequence, okay? Consequence of quantum mechanics, and this is why many scientists were so puzzled by quantum mechanics. Okay, so and then still there are many interesting phenomena that's happening and being discovered. Okay, in small scale object. Okay, so in the sense again, like this is a really probabilistic kind of interpretation. Okay. Okay. So, do you have any other questions up to this point? Okay. So then, let me just kind of describe Bohr model for hydrogen. Okay. So, Bohr suggested kind of atomic model, right? So initially, what he proposed or, kind of hypothesized for atom, there is a, nucleus and then electron is kind of going around, and then he believed that the radius here is essentially given as R. Okay, so this R is 5.3 times 10 to the negative 11th power meter in ground state. Okay, so this one was like what he initially suggested. Okay, but later on, when quantum mechanics was being developed and then Schrödinger equation was being solved, and it turns out that sigma x, okay, the standard deviation of the position, it turns out that is much larger than this suggested Bohr radius. Okay, Bohr radius. Okay. So what does it mean? Like actually, later on, probably will come back to this one. Okay, and it turns out, these are Bohr initially suggested, it turns out that this one was simply the expectation value. Okay, so Bohr model tells us expected value or average value, and then because of quantum mechanics now tells us that sigma x is much larger than R, so that means like we have a probabilistic distribution, and then that like a spreading is much larger than R itself, right? So what that means is that now electron really does not orbit with a given radius. Okay, it has a probability distribution. So in the sense that, like if I actually describe this as kind of probability, this is a center. Okay, R is a 0, and then this is R, and then this one is a probability of finding the electron at any R point. It turns out that it's gonna be a little bit more kind of complex distribution, but it turns out it's like something like this. Okay, something like this. Okay. So it's not exactly like this, but like my point here is that electron can be found even here, or like even if I kind of go there like this, maybe it's like this. Okay. So electron can be found this location with this probability, and the electron can even found here at this probability. But when we evaluate average of distribution, it turns out this R, this is the R, okay? Or R naught here. Like when we say R naught, right, there's a Bohr radius. So, like this Bohr model, that was still a pretty good guess, because he thought that the electron is going to be orbiting at fixed radius, but later on it was kind of corrected such that electron does not really orbit with a given radius. Electron can be found anywhere, but it turns out that average value turns out to be this R, okay, R naught, Bohr radius. Okay, so this is where we introduce electron cloud. Have you guys heard about electron cloud in atomic model? So what does that mean? Electron can be actually found anywhere, okay, within the cloud with some probability distribution. But if we evaluate the average of R, it turns out, that is some known value, okay, in this case, R naught, okay? So the electron cloud concept is essentially coming from, the fact that the position of electron follows probability distribution, okay? Probabilistic distribution, okay? So again, here tells us expected value, and then, later on we kind of found that, the electron does not orbit at fixed radius, okay? Okay, so this one's kind of a interesting consequence of quantum mechanics. And then now, let's look into various potentials. Okay. So U, and then we are going to kind of see how these potentials affect kind of the solution of Schrödinger equation. Okay, so in the sense, first we are going to look at free particle. Okay, so what that means is that now this one does not or not subject to any potential constraints. Okay, nothing is blocking this particle. Okay, so in the sense, we have potential like a barrier 0 everywhere. Okay, so for this one, we are going to apply this one to Schrödinger equation, and that is if psi time independent Schrödinger equation. Okay, we are going to work on just time independent Schrödinger equation because for time dependent one, we are going to simply multiply by the solution of the time dependent part, right? Time dependent equation. Okay, so we are going to work on just time independent Schrödinger equation means like this one is only space dependency, right? And then here we are applying this u equals 0, right? So what that means is that this term goes to 0. Okay, so physically what this means is that when we consider the particle, or well, in quantum world, any particles, any matters have wave characteristics, right? So this particle also has a wave characteristic, and there is no constraint. Okay, so u, this potential barrier, is a 0 everywhere. So what that means is that this particle or wave can freely move around, right, in X domain, right? This is essentially the case for free particle. Okay, and then now we are going to solve this Schrödinger equation. Okay, this one. So then, what is the solution form? Okay, for this second order ODE, it is essentially cosine sine or exponential, right? So it turns out it is, guess the solution form is this one. Okay, IKX. Okay, so this is the solution form for this equation, and then we are gonna now, take because we have to deal with the second derivative, right? So what we are gonna do is we first take first derivative, and then that means minus a ik exponential minus ikx plus b ik exponential ikx, right? And then we have to do one more derivative here, and then when we do that, that is essentially minus a k square exponential minus ikx plus here minus minus b k square exponential ikx. Okay, so here the reason why we have a minus here because I comes out again, right? And then there's I square minus 1. And then here ik comes out, I, you know, that's essentially gives you a negative 1. Okay? So now we got this expression, right? Those square, d square psi over dx square. Now we are going to substitute here. Okay? So now what we are going to do is we are going to substitute here, and then let's kind of express this whole equation in the next page. And then if we write down, there is minus h bar square over 2m minus k square, and here this is a exponential minus ikx plus b exponential ikx equals e psi. Okay, so you know, like the way I did is that, you know, we got this expression, guess the solution form, and then we took a second derivative. Okay, and then here we just substitute here, and yes, the second term is 0, and then this is what we got. Okay, so then look at this part. A times exponential minus ikx plus b times exponential ikx. What is this one? This is simply this part, right? The guess solution form, right? So what that means is that this one is simply psi itself, right? The guess solution itself here. Again, look at this part, and then here. Okay, same. So then now we can rearrange the problem here. That is essentially h bar square k square over 2m psi equals e psi here, right? So then from here, what we know is energy is simply h bar square k square over 2m. Right, that is essentially what we get by solving Schrödinger equation. And then what does this mean? You know, like now we can actually, you know, energy is a very important physical parameter. So now we can express energy in terms of k, right? Because k is wave number, or in 3D domain, we actually call it wave vector, okay? And then this wave number is related to wavelengths, right? So for example, if you look at this expression, h bar is constant, m is a constant, right? Like that m is gonna be the mass of the particle that you are looking at, okay? So we didn't say what this particle is, but for example, if this is an electron, let's say, you know, like because we often use electron as an example, so then this m is going to be mass of electron, okay? And then this k is kind of variable, okay, which is a wave number, and it has it's an inverse relationship with the lambda wavelengths. And then, you know, we can kind of plot how energy varies with wave number. That is essentially parabola, right? Because it has, yeah. So here, parabola. Okay. So, you know, like as you increase, I mean, the precisely speaking, let me see. Yeah, I mean, this one has to be, it has to go through the 0 point here. So this is parabola, okay? So then when you look at this energy distribution, okay, one thing you can notice is energy varies continuously. Okay, do you see that? It can take any energy, right? So energy is continuous. So this is actually an important fact, okay? Note that, because later on we are gonna see continuous, okay? We are gonna see it when energy is no longer continuous, okay? So what that means is that for free particle, okay? So free particle, what does it mean? You know, like when we don't have any potential constraint, okay? We don't have any potential constraint. That means now energy can take any values. Energy can take any values. So in this sense, it's like just bulk object. Okay, bulk object can take any energies. Okay. Yes, please note that. Okay, and then we are gonna now kind of move on here. So with this one, now we can also look at the full solution. Okay, full solution is now psi t x comma t. Okay, so if we get the full solution, which has time dependency, how do we get that? That is essentially space dependent function multiplied by time dependent function, right? This psi x we already obtained here, okay? And then what about phi of t? We also obtained it before. Do you remember? Okay, so this phi of t is, if I kind of go back, maybe many slides here, look at this part, okay? From first set, okay, so here, when we work with this part, we got this solution. Do you remember? Okay, so we are going to use that. Okay, so that is why we are only working with just time-independent Schrödinger equation, because this solution is already given. Okay, so with that, let me just kind of write down here phi of t exponential I e t over h bar. Okay, so here the sign really doesn't matter. So I'm gonna just write down x comma t. There's e I e t over h bar, and then a cosine minus I k x plus b times exponential I k x. And then it turns out that is a times e to the minus I k x minus h bar k over 2mt plus b times e to the I k x plus h bar k over 2mt. Yeah. Okay, h bar t here. Okay.
So were the cosine?
Sorry about that. Exponential. Yeah, this exponential. Yeah. Thank you. So this one has to be exponential. So this expression actually stands for or represents traveling wave. So what that means is that when we actually plot, obviously I cannot really describe in both time and the space domain, but when we look at it, this one is essentially traveling wave. Okay, so that means it's kind of it's moving in x direction or y direction. Basically following this expression. Okay, so this one is a traveling wave, and then this one makes sense, right? Because when you consider a free particle, and then this particle can be represented by also wave, and then if there is no constraint whatsoever on x domain, this will freely move, in x domain, right? So it's kind of a traveling wave, basically in x. So that is essentially the solution. Okay. So this one was the simplest case, right? I mean, free particle. What it means is that even for working with a Schrödinger equation, this u is 0, right? And then now we only deal with these two terms in time-independent Schrödinger equation. But for other cases, we don't have 0 for potential energy. Okay, we can impose certain kind of shapes of constraint, and then we can kind of look into how the particle or wave behave. Okay, so that is essentially what we are going to work on next. So let's look at this one. Okay, so here we just kind of here. Okay, so for this one, now we are gonna look at particle in a one-dimensional infinite potential well. Okay, so what we are gonna work on now is, this is X domain, and then we are putting the wall where this is X equals 0, and then we are putting another wall at X equals D. And then this potential energy is infinity, okay, at both ends. And then we are putting the particle between, X equals 0 and X equals D, okay? So what that means is that, basically you can imagine this as the infinitely high wall, and then this is essentially kind of a infinitely deep well or bucket, okay, and then we are putting the particle within that bucket or well, okay, and then we are going to try to understand how this particle or wave behaves, okay. So imagine this is essentially kind of same as the bucket here, but this wall is infinitely high, and then we are putting the particle inside. Does that make sense? Yeah? Okay. So then we are going to actually look at Schrödinger equation. Again, we are going to just simply write down d squared plus psi dx squared plus u plus psi equals e plus psi here. Okay. So for this one, we have to actually look at three different regimes. Okay. So for example, I'm gonna just write down here. This is essentially, imagine this is a regime 1, and this one, the center part, is a regime 2, and this area is a regime 3. Okay. So just for the simplicity, let us work on this regime 1 and regime 3. Okay. So actually for these two regimes, we don't have to work on solving Schrödinger equation, because we can actually kind of guess, or we can reasonably find the answer by just looking at the physical problem. Okay? So can you find it out? For example, this psi, okay, let's say psi x is equal or less than 0, psi x large or equals 0. When we solve the Schrödinger equation for regime 1, we are going to get the answer, right? And then when we solve this Schrödinger equation for regime 3, we are going to get the answer here. But what would this be? Can you guess? And then really some explanation. What can that be? Wave function in regime 1 and wave function in regime 3. What does it have to be?
Is it not 0?
Why? Question is.
Because it can't be in 1 or 3.
So in other words, what is the probability of finding the particle at any location? That one is essentially determined by probability density function, right? Probability density function. So for example, probability density function is given as psi star psi, and then this psi star psi is the probability and the probability of finding this particle in region 1 and region 3 is 0, right? Because it's infinitely high. If you put something inside, can you find this one outside here? No, right? So then this psi star psi must be 0 in region 1 and region 3, and because of that, psi must be 0. Does that make sense? And that is kind of our argument. So we already found the solution for region 1 and region 3, and then we have to find the solution for region 2. But for that, I guess we'll continue next Monday, right?